Okay, I want to look at motion maps. Motion maps are a way of showing the motion of an object, and they're a way of showing how that position changes as a function of time. We can also use them to sort of figure out velocity and even acceleration. We don't do that too much, but I think motion maps are really useful. And what you should have done before this is put a video into Logger Pro, and hopefully you've drawn the right conclusions about the positions of the dots, the regular dots that indicated position of the balls. Well, let's have an example here. This is a ball that's rolling to the right. I roll it there and it's going pretty fast, and it's on grass, and maybe it's a croquet ball or something like that. And it's going to roll, and eventually it's going to come to a stop. Let's just say it comes to a stop there. Well, it's not going to just roll really fast and then just stop. It's going to slow down continually. Motion map is a way of, think of it like a strobe light. A strobe light lights up once every certain amount of time, a fraction of a second. And so maybe what happens is we look at the very beginning, and here's t equals 0 seconds, okay? And let's look at that every tenth of a second. Maybe after a tenth of a second, it's there. Okay. Well, it's slowing down. So in the next tenth of a second, I'll just put here. Maybe after another tenth of a second, it's there. Okay, it's not going to travel as far. And so what we get is these getting progressively closer together in our mind, and then finally it stops. And that's really a motion map. So 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, and maybe after 0.9 seconds it stops. And that's a motion map. A motion map of this would look like this. So it's equal time frames. I'm not going to get it to line up just right. Okay, so it's equal intervals, equal time intervals. Where is it after each one of these equal time intervals? Equal time intervals. And you can see here, fast, because it moved farther in that small amount of time. And we could think of that as a displacement at that point. There's the displacement there. For the same amount of time over here, the delta x, the change in position, is slow if we just look at that interval. In other words, the change in position during that interval. Okay, so close, slow. Oh, let me put it this way. Close, small delta x, and so small speed. And we'll talk about velocity later. Far apart, big delta x, big speed. So we can draw conclusions about the motion of objects based on looking at their motion maps. What do you need to be able to do is represent an object that's moving in a motion map. It doesn't have to be perfect, but it has to have the right, allow us to draw the right conclusions. And you also want to look at a motion map and say what's going on. Okay, so let's try one here. Here is an object, and I'm just going to do it like this. So it's going like that, and then it's going like that. Okay, and you can see at the bottom, big velocity, fast, and up near the top, slow, because the dots are closer together. Okay, and then back here it's fast again, but moving in the other direction. That's if you throw a ball in the air. That's what it looks like. How about this? Okay, that's something that's slowing down. So fast, I'll just put fast, slow, fast. So slowing down here, assuming it's moving to the right, I should put an arrow in there. slowing down, speeding up. Up. Okay? Now finally, let's take a look at it here. Oh, and by the way, we can draw, since that would be the displacement for that interval, that would be the displacement for that interval, and so forth. These actually are also very similar to the velocities, so those arrows kind of indicate what the velocities would be. So now let's look at, here's somebody shooting a basket, and it's in 2 dimensions. If you look at this, though, you can see here, faster, then up at the top, slower, faster. And this was done in Logger Pro. And I'm not going to show you the graphs. I'll show you what they end up looking like. But what's really interesting about this motion is, yes, that is the change in position. But if we look at the horizontal change in position, it's about the same every time, even up at the top. That horizontal delta x is consistent the whole time. That means horizontally, that's terrible, constant speed. Vertically, though, if we look at the delta y there, that's pretty big. Up at the top, it's almost nothing. Barely moves up at all. So vertically, slows down and then speeds up in the other direction. Slows down in the positive direction, or the up direction, speeds up in the down direction. What this actually ends up looking like, if you look at horizontal position versus time, x versus t, it's a constant velocity. Oh, I'm drawing that wrong. It's a constant velocity, so it looks like that. Okay, if you look at the vertical position versus time, y, it's constantly changing. Okay, when we get to velocity, we'll see why that's interesting, but it allows us to solve what looks like a calculus problem. I mean, you've got this parabola, right? It's really hard to solve. Now, it's really easy. What you do is you solve a constant speed or constant velocity problem horizontally, then you solve a constant acceleration problem vertically. So what you should be able to do, should be able to interpret motion maps and draw an approximate motion map. Hope this has helped.